In the early 1770s, three scientists, isolated across Europe, each extracted a mysterious air that made flames roar and mice live longer. But only one would truly shatter chemistry's deepest law. Was this new gas a hidden element, or a trick of old theory? The real story behind oxygen isn't just about who found it first. It's about a race where the rules of science itself would change, and where someone's groundbreaking proof would stay secret for years. The stakes are a public battle that would end a scientific era and ignite a revolution. So who really discovered oxygen, and what made this invisible gas worth fighting for? In the early 1700s, the science of air seemed settled. Georg Ernst Stahl's phlogiston theory explained why wood burned and metals changed in fire. The idea held that every flammable material contained phlogiston, an invisible principle released during burning or calcination. When a metal was heated and turned to a powder called calx, it was thought to have lost its phlogiston to the air. For decades, this model fit what chemists observed. Flames needed air, and once a room's air became saturated with phlogiston, nothing would burn. But a stubborn problem refused to go away. When metals such as tin or mercury were heated in a closed vessel, the resulting calx actually weighed more than the original metal. Instead of losing something, the metal gained mass. The phlogiston theory struggled to explain that. If phlogiston was escaping, what accounted for the extra weight? Some suggested phlogiston might have negative mass, but the numbers never added up. Meanwhile, a new generation of experimenters began to question whether air was really just one substance. The invention of the pneumatic trough by Stephen Hales in 1727 made it possible to trap gases released during reactions. Chemists could now collect airs over water or mercury and test them directly. They noticed some gases extinguished flames, while others made flames burn brighter. These experiments hinted that air was not a single, featureless element, but a mixture with hidden components. The mass paradox, together with improved gas collection tools, set the stage for a deeper search. Chemists were about to discover that the air around them held secrets that could overturn old theories and reveal the real engine behind fire and life. Carl Wilhelm Scheele worked in the back room of a small apothecary in Köping, Sweden, juggling prescriptions by day and experiments by night. Between 1771 and 1772, Scheele heated a series of solids, potassium nitrate, manganese dioxide, and mercuric oxide. Each time he captured a colorless gas that made flames leap higher and brighter. He called it fire air. In his notebooks, he described how this gas allowed a mouse to survive far longer than in ordinary air, hinting that it was the true sustainer of life and combustion. Scheele's approach was anything but accidental. He repeated the process with different substances, showing that whether he used saltpeter or manganese minerals, heating drove out the same remarkable gas. This was not a one-off curiosity, it was a reproducible phenomenon. Scheele's careful records, later scrutinized by historians, placed these discoveries years before anyone else published similar results. Yet his findings remained locked in Swedish manuscripts, circulating only among a few correspondents and trusted colleagues. Despite clear evidence, Scheele still interpreted his fire air through the lens of phlogiston theory. He imagined air as a mixture, fire air supporting burning and foul air left behind. His experiments, however, pointed to something altogether new, a component of air that was both measurable and essential. Scheele's work had quietly cracked open the mystery, but without publication, the wider scientific world had yet to realize what he had found. On August 1st, 1774, Joseph Priestley stood in his modest laboratory in Calne, Wiltshire, sunlight pouring through the windows. He positioned a lump of mercuric oxide, known then as red calx of mercury, inside a glass vessel. Using a 12-inch burning lens, he focused the midday sun onto the powder. The heat triggered a transformation. Tiny beads of liquid mercury began to form, and a colorless gas collected above the residue. Priestley carefully trapped this gas over mercury using his pneumatic trough, a technique that allowed him to test its properties directly. He brought a candle close to the mouth of the vessel. The flame leapt to life, burning with a brightness and vigor he had never seen in ordinary air. Curious, Priestley inhaled a small amount himself, later writing that his chest felt peculiarly light and easy for some time afterwards. He repeated the test with a mouse, watching as the animal survived far longer in this new air than in the atmosphere outside. Priestley named the gas dephlogisticated air, believing it was pure air ready to absorb phlogiston from burning materials. He immediately recognized the significance of his discovery and set out to share it. Within months, he published his findings in the first volume of Experiments and Observations on Different Kinds of Air, released in 1775. The book described his apparatus, his methods, and the dramatic results of his tests, making Priestley the first to announce this new kind of air to the scientific world. His work spread quickly through the networks of the Royal Society and beyond, transforming a private experiment into a public claim. October 1774 found Joseph Priestley in Paris, seated at a dinner table with some of the city's brightest scientific minds. Among them was Antoine Lavoisier, already known for his sharp questions about why metals gained weight when heated. The room buzzed with conversation as Priestley, still energized by his recent experiment, described a gas he had produced by heating red calx of mercury, a gas that made candles flare and mice breathe easy. He called it dephlogisticated air, sharing every detail of his method, from the burning lens to the mouse tests, as casually as if recounting a travel story. Lavoisier listened carefully, his mind fixed on the puzzle of combustion. For him, this was more than a curiosity. Priestley's account offered a possible answer to the mass gain that had defied explanation for years. That evening, Lavoisier resolved to repeat the experiment himself. Within days, he was heating mercury calx in his own laboratory, collecting the same remarkable gas. He weighed every component before and after, determined to find out exactly what was happening. The exchange at that Paris table was not just a meeting of personalities. It was a handoff from spectacle to measurement. Priestley's vivid observations became Lavoisier's data points. The conversation set off a chain reaction. Lavoisier would now use his balance and methodical approach to test, not just what air could do, but what it was made of. The story of oxygen was about to move from the realm of marvel to the discipline of numbers. Antoine Lavoisier set a piece of tin and a precise measure of air inside a sealed glass vessel, then placed the whole assembly on a balance. As the tin was heated, it transformed into a white calx, gaining weight as the reaction progressed. When the vessel cooled and was opened, the air inside had lost exactly as much mass as the tin had gained. 93 grains of tin became 110 grains of calx, while the air dropped from 174 to 157 grains. Lavoisier's April 26, 1775 memoir laid out the results in detail. The balance recorded every change. The evidence was unyielding. Combustion did not release anything mysterious. Instead, part of the air was joining the metal. The phlogiston theory could not account for the arithmetic. By the late 1770s, Lavoisier was not satisfied with just proving that air had a vital component. He wanted a name that captured its essence and unified his new understanding of combustion, respiration, and rusting. Drawing on Greek roots, he chose the word oxygen, meaning acid generator. At the time, he believed this new element was found in all acids, a theory that would later prove only partly true. Still, the name stuck. The concept of oxygen let chemists see burning, breathing, and metal calcination as variations of a single process, substances combining with this active part of air. Lavoisier's naming brought scattered experiments under one idea, turning oxygen from a laboratory curiosity into the foundation of modern chemistry. The irony remains, the name outlasted the theory that inspired it. Every breath, every flame, every heartbeat depends on a discovery made in secret, debated in public, and still unfolding in labs today. Oxygen shaped our world, and its story reminds us that even the air we take for granted is a revolution in progress. Thanks for watching.